Scientists are looking to use heat pipes to distribute cooling fluid instead of mechanical pumps, not just on orbit, but also here on Earth. Now, this study on the space station is called Constrained Vapor Bubble, and what is learned could lead to better designs of high-tech devices. Our space station colleague and commentator Lori Meggs caught up with the co-investigators to learn more about this study.
One way to describe it is, well, first it has two aspects. It has a basic science interfacial phenomena study, and it's also an applied study. So just quickly to give you some idea, if you take a capillary tube on Earth, put it in a liquid, the liquid does not go up the capillary tube very far. In our case, we have a capillary tube that has a square cross-section with sharp corners. In that case, the fluid would go further up the capillary tube, but not very far on Earth because of gravity. Now, if you were to take this into microgravity, all of a sudden it doesn't have to overcome gravity, and it would keep going until it emptied the bottle. And now that fluid can flow towards a heat source in order to cool the heat source. So you get evaporation where you get the cooling. Now, in our device, it's closed and it's underfilled, so you have a vapor bubble in there. So the liquid is in the corner, the vapor bubble is in the central part. So at the hot end, you get evaporation, vapor flows down the center, the vapor bubble, to the cold end where it condenses and then is sucked back. The big thing for microgravity, and in fact even on Earth, is you do not need a pump. So you can have a cooling device, evaporation, condensation, to cool something like a computer or some heat source in a satellite without a pump. So you don't have to worry about the pump breaking down. You don't have to worry about putting the pump up in microgravity.
And it wasn't as you thought, right? Some surprising results.
Oh, yeah. There were a lot of mathematical models that have been developed to explain heat pipe performance, but all the models are, in essence, approximations to what would occur. And so when we ran the experiment in microgravity, we got a lot of unexpected results. On one hand, several years ago, we observed boiling in a heat pipe that shouldn't have actually existed at the extent that we observed it. And then this past year, we sort of finally understood what the images were that were coming down from ISS in our experiment. As you put more heat into a heat pipe, all of the models and people's experience from measuring temperatures says that the hot end should actually dry out and the liquid should be removed basically from the dry end. And what we observed up on ISS was exactly the opposite behavior. We started to suck liquid all the way up, and basically we flooded the hot end. If all we did was measure the temperature profile, the temperature profile is indistinguishable between dry out and this flooding phenomena. So it was only in going into microgravity and actually being able to map the entire liquid vapor interface that we could observe this phenomena and then understand the underlying interfacial phenomena and fluid mechanics that actually gave rise to why this would flood.
So as a professor, you're thinking, oh, are you excited that it didn't do what you thought it would do, or are you kind of disappointed that it wasn't as you thought?
Well, let's see. It's very complicated emotionally. First, we were angry because when we observed it and it wasn't what we expected, we thought the people that built it contaminated the device and the experiment was worthless. Then once we really understood that that wasn't the case, of course, you get excited to observe something that no one had really predicted before and still can't really predict now mathematically. So
how does that translate to us on Earth? What you have learned and what you've seen, are there Earth applications to this?
Well, sure. It makes people rethink what might be going on in heat pipes they build, since everybody builds a heat pipe with essentially a metal shell associated with it. And so there may be flooding that's going on that people don't understand. And it's up to us to analyze, say, our data and try and give them a temperature signal that would say that, yeah, your heat pipe is not drying out, your heat pipe is flooding. It can also bring about, entirely new kinds of designs for the internals of heat pipes to prevent this flooding phenomena occurring. And in CVB2, we tried one of those experiments by adding a small amount of a component that had a slightly higher surface tension and a slightly lower vapor pressure. And it turned out that we could actually use that kind of process to sort of break the phenomena that we saw in CVB1. We hope to fly some more experiments, especially with higher ratios of liquid mixtures. It's important not only for the development, say, of heat pipes, but important for us as chemical engineers to understand, say, how the distillation process works. And no one's ever really looked into distillation with the kind of characterization ability, say, that we could do in this heat pipe experiment aboard the ISS.